Right. Assalamualaikum and good day, everyone. So we continue with our discussion on the previous final exam examples taken from September 2015. So the question states that refrigerant R134A is held in a cylinder fitted with a frictionless piston so that the gas can be slowly compressed from an initial pressure of 99 kilopascal to a final pressure of 305 kilopascal. The initial temperature and volume are 24 degrees Celsius and 0.0453 meter cube. The compression process is such that PV power of 1.3 equal to constant. The internal energy is given by U equal to 1.5 PV. Determine the change of internal energy in kilojoule over kilogram, the work input in kilojoule, and the heat transfer of the compression process also in kilojoule. All right, first we are going to look into the substance given by the question. In this question, it is given refrigerant 134A, which in our discussion in MEC251, normally R134A, the analysis will be conducted by using the property tables. But in these particular examples, since it is stated that it is a gas, thus we are going to use the ideal gas equations to solve these particular problems. All right, so um, since we already decided that we are going to use all the formulas and equation based from the ideal gas, then next we are going to extract all the data given by this question. Okay, so given here is the initial pressure P1, 99 kilopascal, final pressure P2, which is 305 kilopascal, and then the initial temperature and volume also are given, which is T1 and also V1. So you can write all these informations as such. State 1, P1 equal to 99 kilopascal, and then T1 equal to 24 degrees Celsius. Like I always mention to all of you, we're going to convert the temperature into Kelvin. So it's going to be 297.15 Kelvin. And then we also have given from the question is the volume as T1, which is 0.0453 meter cube. So next what we have is informations from state 2, which is only the pressure 305 kilopascal. And given the correlation based on the polytropic process is PV, power of 1.3 equal to constant. And also the internal energy can be determined by using this correlation 1.5 PV. Right. So if we look into the items that were asked by this question, you need to determine the change of internal energy. So we are going to solve this referring to the ideal gas solution that we have learned in MC251. Thus, the change of internal energy will be given by CV times with T2 minus T1. And then the work input, since we know that this is polytropic process because of we have the relation over here, PV power of 1.3 equal to constants. So this will be referring to polytropic, right? Thus, the work input can be determined by using this formula. Okay, P2V2 minus P1V1 divided with 1 minus N, and N is the polytropic index. Based from the question, the polytropic index will be 1.3. Alright, so the last one that they requires you to determine is the heat transfer for the compression process. So the heat transfer of the compression process will be given by from the NFE, non-flow energy equation that I always told you guys, Q minus W equal to changes in the internal energy. Thus, the heat transfer will be changes in the internal energy plus with the work input, right? So let's solve this question, right? Okay, based from this relation, we can write the relation between state 1 and state 2 as such. So from this, what we actually want to determine is the volume at state 2. Okay, so from here, V2 is equal to P1 V1 power of 1.3 divided with P2 square root 1.3. So we're going to get the value for V2. So you are going to get 0.0191 meter cube. Alright, so next we want to determine the change of internal energy, item 1 that requires by the question. So the change of the internal energy is given by one point five P2 V2 minus 1.5 P1 V1. Alright, although I wrote to find the change of internal energy as such. But since it has been given from the question on the correlation for the internal energy, so we just use this one. Okay, so based on the data that we have here, so we can see that we have the value for P2, V2 already being determined, and then we have the value for P1 and also V1. And when you calculate, you're going to get the value for the change in the internal energy is 2.0112 kilojoule. As can be seen, the question requires you to find in terms of kilojoule over kilogram. Therefore, you need to divide the changes of the internal energy that has been calculated with the mass. So in order for us to determine the mass, we are going to use the ideal gas equation of state. So we have the value for P1, we have the value for V1, we have the value for T1. However, we doesn't have the value for the specific gas constant for refrigerant 134A gas. For this, you can refer to the property tables. Table E1, if you can see there, we have the substance of R134A, and then the value for the gas constant will be 0.08149 kilojoule over kilogram Kelvin. Okay, so when you substitute with all the data that we have, you're going to get the mass is 0.1852 kilogram. So in order for you to get the internal energy, the change of internal energy in kilojoule over kilogram, so you're going to divide delta U with the mass 2.0112 kilojoule divided with 0.1852. So you're going to get over here, the answer will be 10.8596 kilojoule over kilogram. Okay. So the second items is the work input. So just insert the data. Okay. Work input equal to P2 V2 minus P1 V1 divided with 1 minus N. So we have the work P2 is 305, V2 will be 0.0191 minus P1 99, V1 0.0453, and then divided with 1 minus 1.3. So for this, you're going to get the work is equal to negative 4.4693 kilojoule. Okay, and then the third question is the heat transfer. And we know that for the heat transfer is equal to changes in the internal energy plus with the work. So it requires us to determine to calculate in the unit of kilojoule. So for this, the internal energy that we're going to use is this value, and for the work will be this value. So heat transfer is equal to 2.0112 kilojoule plus with minus 4.4693. So you're going to get the final answer is minus 2.4581 kilojoule. Right, so that's it for this question.